I want to talk to you about the power of functional decomposition and, of course, systems thinking more general. And one of the people that Charlie acknowledged in his talk, Dr. Sidney Doe, one of our really stellar graduate students who's now working on the Mars sample return mission at Mars. And so I think it's very good to keep track of career progression as well. So functional decomposition, what is it? You know, as engineers, as designers, we often, as humans, we often have a tendency to first focus on the form, you know, the physical things that we see, we can touch, because function is kind of, in some sense, invisible. It's more intangible. And I want you to think about function first, because it's really the functionality of things, whether they're products that we use in our daily lives, whether they're systems that we use, develop to explore the Earth or explore space. It's really the functionality that we want to think about. And there's often many different ways, different elements of form to satisfy the same function. So functional decomposition is a way to, it's a method for designing complex systems where we first focus on the function and then break it down to sub-functions. So let me try to explain how functional decomposition works and how powerful it really is. So first of all, we're talking about systems here. What are systems? Systems are sets of entities that can interact with each other to accomplish a function that could not be accomplished if we just have the sum of the functions of the individual entities alone. And the word that we use in system architecture for this is emergence. So the higher level functionality emerges out of the entities' interactions at the lower level. And emergence is really magical in a sense. The key concepts here, the key words are form. What is form? It's the physical or informational embodiment of the entities of the system. The function is what the system or the entities does, the actions acting on form. And then finally, concept. What is concept? It's the mapping from function to form at various levels of decomposition. And I want to just give you this as an example of emergence. So an element of form is a beam. Okay, let's think about a beam. It has the ability to carry forces and torques and so forth. And we're going to have an input force on the left and we have an output force on the right. What is the function of the beam? Would anybody try to give an answer? What is the function of a beam? Those of you inclined to structural mechanics. Anybody have a suggestion? What is the function of a beam?
Ollie, check the chat. Many people are putting answers here.
Okay. Could somebody read the chat for me? Because I have a little trouble seeing it right now.
Yeah, yes. A one is to transfer torque, Ollie.
Yeah. Yeah, that's basically right. So it's basically transferring the bending moment, carrying a bending moment. And then let's look at a support, also sometimes known as a pivot. What is the function of a pivot? A pivot allows for rotation, but suppresses translation. Now let's put the two together. So we're combining the beam with the support or the pin or pivot. What is the function that we now get? So what you're looking at is what we call a lever typically, but the emergent function is amplification of force. So think about that. We've created, the lever is there to amplify force, and that functionality emerges from the fundamental building blocks. And that's how engineering works, of course, for much more complex things, as we'll see. So the structure enables, but the emergence happens from functional interactions. So let's take a look at some examples. And one of the key pedagogical things that we need to reinforce, whether that's at the doctoral level, at the graduate level, in high school, even in middle school, and perhaps even in elementary school, is this clean separation of form and function. It seems obvious, but it's so foundational for design engineering, for system architecture, for the work that we do in this program. So if you think about a factory, that's the form. What is the function? Well, assembling cars. And you'll notice that when we talk about function, we use verbs, but in particular, we use the gerund form of the verb, assembling. So always ending in ing, that's called the gerund form. Assembling cars using a factory. Okay, here's another example. So we have a team here. There's 3 people in this team, and they're discussing something. What are they doing? What is the function of the team? Or could have different functions. But in this case, it's making a decision. So making decision is the function using a team or with a team. And you'll also notice that the benefit comes always, always, always from the function. And the cost is always incurred by the form, the elements of form. One more example, this is from our own bodies, from biology. This is the cardiovascular or the circulatory system. Cost, of course, you know, it's ATP, it's energy consumption in the human body. What does it actually do? What's the function of the circulatory system? Fundamentally, it's to supply oxygen to our cells. Supplying oxygen using the circulatory system. Okay, so hopefully that the central importance of emergence in system design cannot be overstated. And so emergence occurs when function of the entities and their functional interaction combine to produce something new, a new functionality, which is more than the sum of the parts. And you see in this diagram, we have even drawn a system boundary, that red dashed box. Those entities inside that red dashed box are entities, they're the subsystems and components of our system, and we interact across the system boundary with objects or elements outside the system boundary to create this emergent function. Now, what we want to do is we want to zoom inside of this red dashed box and expose the internal entities, so the sub-elements or components of the system. So going back to our 3 examples, the factory, okay, we've now decomposed the factory into 3 elements of form, and they're typically stations. If you think about an assembly line, station 1, station 2, station 3, and what happens at these stations, the overall function is assembling cars, but you can now subdivide that into, you know, integrating the drivetrain, integrating the body, integrating the interior, and so forth. And to really get to the bottom of things, to entities that cannot usefully be decomposed further, we often need 3 or 4 levels of decomposition, as you'll see. So let's decompose our team. Well, that's the team members. Let's say Mary, John, and Joseph. And so each of them have a particular function as part of their team. Sometimes we call that their job description. So Mary's job is collecting information. John is developing values, and Joseph is synthesizing and evaluating the information. Together, they make a decision. If we decompose the circulatory system, we have the heart, the lungs, and the capillaries. What does the heart do? Pumping blood. What do the lungs do? They exchange oxygen and CO2 with the air. And then our capillaries exchange oxygen and carbon dioxide. I'm going to talk about carbon dioxide again in a few minutes with our organs. And so we can go into greater level of detail, but you see the logic here of functional decomposition. And basically what we're doing here is we're applying decomposition to systems that exist in nature, or that that already exist. And we're going to, of course, use that logic for designing new systems, coming up with new solutions to these epic problems that Charlie was talking about. So coming back to our example of the lever, you can now see that the beam is essentially there to carry moment and also shear forces, of course. And then the support is there as to react the forces into the base, into the ground. And so you'll have the reaction forces that create an equilibrium, force equilibrium. So hopefully with that introduction, very basic examples, but the notion of separation of function and form, the notion of decomposition multi-level, and what functional decomposition actually is hopefully a little bit clearer. So one of the epic problems that we have addressed in this program in the past, and that continues to be a grand challenge for us, is a Mars habitat, habitation on Mars, creating an off-world settlement where humans can live. And so we're talking about the function of sustaining the human crew and also performing science. We don't want them to just, survive there on the Martian surface, but doing useful thing like creating new knowledge, performing science. And so that's what we call sustainable exploration of Mars. And we'll come back to those two functions, sustaining human life and performing science on Mars. So let's focus on the sustaining function, sustaining humans on Mars. You've seen many different Mars surface system concepts over the years. And it's really about human-centric, focusing on what does it take to sustain humans on Mars? Well, water. You've heard this, the water is the elixir of life. It cannot be overstated. So we have to manage the water. We have to provide food, nutrition. There's caloric requirements. We have to provide shelter, protect from dust, radiation, and the very low pressure environment. Humans produce waste, and so we have to manage that waste, liquid and solid waste, gas, also in the form of gases. And then in order to manage water and provide shelter, we need to provide power, right? Energy, the time derivative of energy is power. And so all those processes, managing water, providing shelter, cannot happen without managing power, which is a derived function. And on the right side, transportation. You see on this picture, there's a pressurized rover, there's astronauts performing extravehicular activities or EVA. So transportation functions are also critical. And, if you think about it, those functions these are the same fundamental functions that we perform on Earth as well in our cities. And so on the lower left, you see one of the interesting cities that we've studied over the years is Masdar City in the United Arab Emirates. This was a city designed from scratch to be sustainable. And the UAE, by the way, also just sent their first mission successfully to Mars. There were 3 missions that just arrived at Mars in this launch window. Of course, our very own Perseverance rover, a US mission, the Chinese rover that just landed, and the UAE mission. And so it's kind of getting crowded already at Mars. So to facilitate this work on functional decomposition and system architecting, we teach and use a methodology, a language essentially, a system modeling language called OPM, Object Process Methodology. And this language, I don't take credit for it. I'm just a user of it, but it's extremely powerful. It was created by Professor Dov Dori at the Technion, which is the Israel Institute of Technology. And what's powerful about OPM, well, first of all, since we first started using it, it became an ISO standard. So it's ISO standard 19450. And let me put in the chat, those of you that just want to play around with it, I'm going to put a link for you in the chat to the sandbox for OPM. So you can just play around with it. You can't save a model, but you can create one and create a screenshot of it. So if you want to go there and just see what it looks like, there's a really nice cloud-based tool for it. And so it has a graphical and a verbal method to distinguish form and function and develop system models. And it's based on the idea that everything in the world is a thing, either an object or a process. So objects are the elements of form, and processes transform the state of the objects. So we talked about humans, that we need to nourish them. So the object in this case is the human, the process is nourishing, and the state that is being changed is changing the human from being in a state of being hungry to a state of being nourished or satiated. And so you can see in a graphical form, the object human its state is being transformed from hungry to satiated by the process of nourishing. We can hide the details of the state transformations and just talking about effect links. That's a bidirectional arrow. And we can just suppress the representation of the objects and talk about nourishing humans if we want to keep it really simple. But what is a function? A function primarily is a process acting on an object to either create or destroy the object or consume the object, or more frequently, to change its state one or more states. And so in object process methodology, we have different types of links. We have structural links, which are links between objects. And some of this gets a bit abstract, but I found honestly that anybody can learn this. A middle school student can learn this. A high school student can learn this. It's very, very helpful to clarify the thinking. So structural links are decomposition. So a human can be decomposed into a head, a torso, and limbs. Exhibition links, which are attribute links, essentially. So a human can be described by their gender, their height, their weight. Specialization, which is a variant of, so a human can be specialized, can be an infant or an adult. And then instantiation, John, Mary are two instances of humans. And these are, you recognize some of these are in computer science, concepts like inheritance, decomposition, exhibition. These are very important types of relationships between objects. And then procedural links, these are foundational links. The consumption links means an object is being consumed by the process. A resultee link means that a new object was created out of the process. So the arrow points out of the process into the object, like producing metabolic energy as a result of the nourishing process. Instrument links, like a means of transportation, a pressurized rover, like you just saw in that picture, is an instrument of the process of exploring. And then we have agents, so-called agents. So the humans in this case are the agent of the exploring process. That's this link with looks like a lollipop filled in. And then we have invocation links, which are links between processes, where one executing one process invokes another process, meaning creates a need for another process, which is a kind of functional relationship. So I'm going to use this to show you how we can use functional decomposition to think about, say, for example, keeping humans on Mars alive in a really systematic way. So the first two, the consommé and the resultee link, really talk about function. And when we think about how that function gets fulfilled, how it's enabled, it's the instrument and the agent link that become crucial. Because you're assigning the concept. So the steps for doing functional decomposition of a problem are that you first always need to have a problem statement. And I think, Charlie, you spend a lot of time on this. Every year, every time a new EPIC challenge is launched, significant amount of time is chosen on the problem statement itself to make sure it really is not a trivial statement. It's a challenging statement, but it's not utopian either. So in this case, sustainable human exploration of Mars. Then the second step is to assign a concept. In this case, we're assigning the concept of using a habitable space to accomplish the function of sustaining humans. And you see that in the system boundary, we have the humans, we have the sustaining process or function, and we have the notion of habitable space. And so we're starting to zone in on how we're going to achieve that high level, how we're going to solve the problem. And then step 3 is now the key of breaking down this high level function of sustaining humans into the sub functions that are required. So performing functional decomposition of sustaining humans, which introduces the internal objects that act on lower level processes, enumerating the attributes of the habitable space concept that affect sustaining humans, and then enumerating the attributes that characterize the sustainably attribute of exploring the process itself. And so we're going to now start breaking things down into greater levels of detail. So the habitable space itself, with the attribute link, can be described by its volume, its shape, its internal arrangement, or what material are you using for the walls. Sustaining humans has different dimensions. Physiologically sustaining, that's what we all think about first, water, food, oxygen, etc. But also psychologically sustaining humans. And we always need to think about contingency scenarios or emergencies. So we think about human consumables, metabolic output, metabolic waste, and then sustainably exploring. Immediately, we have to say, well, how many humans, what's the number of crew, and what mission duration are we talking about? And the fact that we're, in this case, interested in exploring Mars. So that's our level 1 functional decomposition. Having accomplished that, we can say, okay, well, now let's go to further levels of detail. What does physiologically sustaining actually mean? So we're now taking that high level function and we're doing functional decomposition to expose the lower level functions of physiologically sustaining. So for example, the nourishing process, absolutely, we've talked about that. Preventing muscle atrophy, that invokes a process or a function called exercising. That's how through exercise, we prevent muscle atrophy. And remember, Mars only has 38% gravity compared to Earth. So cardiovascular deconditioning preventing and muscle atrophy preventing are both facilitated through exercising, including bone degeneration preventing. We need to manage the thermal environment, the atmosphere, protect from radiation and micrometeorites. We also need to prevent humans from getting bacterial or viral infections. And the other function was to psychologically sustain humans, meaning manage their level of stress. How can we do that? Through entertaining, lighting, sleep accommodating, noise managing, connecting to family and friends back on Earth or on Mars, and managing vibrations. You can see that the attributes of Mars, the 38% gravity I was talking about, the surface temperature, the low density of the atmosphere, the 95% CO2 atmosphere, the high dust environment, those are all attributes. And you see, we start to link them all together in very detailed ways. Oops, I think I just went backwards. And Charlie, I'm just gonna take a couple more minutes if that's okay. And so by mapping now the internal attributes and subsystems against the detailed functional decomposition, against the attributes of the environment that we're working in, we can reveal all of those relationships. And notice that I haven't yet said how exactly we're going to achieve these functions. These are generic ways of decomposing the problem before we actually pick a particular technology or type of material and so forth. But eventually, at level 3 and level 4 of the functional decomposition, we have to start picking technologies. And that's where our engineering design solution and creativity come in. And that's what Charlie was saying, is where younger students that haven't yet preconceived notions come up with such great and unusual ideas that we want to harvest here. That's the key idea. So just to give you an example of a level 4 concept, one of the things we need to do is remove CO2. We exhale, with every breath we exhale CO2. We need to be able to remove that CO2. Now we can do it in different ways. We can do it physico-chemically through adsorption and desorption, or we can use it with plants by growing plants who basically perform photosynthesis and does the CO2 removal bioregeneratively. Two different ideas, two different concepts, same high-level function, CO2 removing. Okay, so the first one is a kind of one-to-one concept. Plants, of course, are a cross-functional concept. And so the other thing I will say, which is really cool in this ISED approach, is the parallels to curriculum planning. So all of those things we've talked about, understanding human physiology in space, heat transfer, chemistry, fluid dynamics, structural engineering, all of those key concepts require knowledge. There's governing equations, there's key principles behind it that can be taught at every level. You can teach heat transfer to a middle school student. You can teach heat transfer to a high school student, but you have to find the right level of detail and abstraction. So heat transfer through convection, that's when you get into thermodynamics, that's when you get into the building blocks of fluid dynamics, and that's where we can also connect to great resources like Khan Academy, for example, which is still used a lot and continues to grow. And so you see that by taking these high-level challenging and doing the functional decomposition, we can now start mapping it to concepts that you can learn in detail with exercises and also exercise your creativity. So Charlie, I know I'm running out of time. We're kind of on a compressed timeline here. I just wanted to show you something really cool that happened in the last month. And since we talked about Mars, we talked about CO2, we're very proud at MIT to be working with NASA on the first ever demonstration of in situ resource utilization on another world. The MOXIE experiment on the Mars Perseverance rover has successfully demonstrated already in a couple of test sessions that we can actually producing oxygen on Mars by splitting the carbon dioxide molecules using a process called solid oxide electrolysis. This is on this chart, the MOXIE experiment. It's roughly the size of a shoebox. You can see it sits on the starboard side of MOXIE, and we've already produced very, very high, in the high 90s% pure oxygen on Mars using this approach. That's new. In 2012, that was just a hope we had. We have done it. And the idea for doing this came exactly out of this kind of process of system engineering and functional decomposition. So to summarize, we've talked about system, form, function, and concept, the power of emergence through functional interactions, the fact that the benefit of our systems comes from the function, but the cost accumulates in the form. Systems analysis maps from form to function. System architecting goes from function to form. And functional decomposition of the Mars habitation problem, as an example, can guide idea conception or idea generation and engineering development. Thank you very much.